Good afternoon, dear participants of the Third International ProfIT Conference. Let me introduce myself. My name is Skob. I am the presenting author of the report on the topic, Mathematical Modeling of Gas Admixtures, Release, Dispersion, and Explosion in Open Atmosphere, on behalf of a team of authors from the Zhukovsky National Aerospace University in Kharkov, Ukraine. The aim of the work is using means of mathematical modeling to make an analysis of gaseous hydrogen mass concentration and pressure fields in the area of accidentally spilled liquid hydrogen after its evaporation and explosion. Physical processes of gas-air mixture formation as a result of accidentally spilled liquid hydrogen evaporation and subsequent explosion in the surface layer of the atmosphere can be considered as an object of the research. The subject of the study is a mathematical model of the process of evaporation of liquefied gas with specified rate from the surface of the spill spot and subsequent explosion of hydrogen air cloud. An explicit time-dependent finite difference first-order approximation Godunov method is used as a research method to solve the problem. The relevance of the study is determined by the need of community of experts in the field of risk assessment of high-risk industrial enterprises in reliable and effective mathematical models that will allow simulating complex physical processes that arise during an emergency release of explosive gases into the atmosphere. Such models should replace expensive physical experiments for analyzing and predicting the consequences of an emergency explosion on the environment. The developed mathematical model of gas release and explosion in the atmosphere was validated using data from physical experiments. Statistical indicators of model quality are within normal limits. The computer information system that implements the mathematical model was verified for various initial data and finite difference grids and showed the ability to obtain a stable solution. The evaporation of liquefied hydrogen from the surface of an emergency spill spot with a given intensity is considered. The gaseous admixture forms a gas-air cloud with the air, which moves under the influence of the wind and gradually dissipates. The system of differential equations of motion of a two-component gas mixture includes the laws of conservation of mass, momentum, and energy of the mixture, supplemented by the law of conservation of impurity mass. The equation of state of the mixture closes the system of equations. To simulate the process of evaporation from the spill spot, Godunov general calculation scheme is used, which has been generalized for the interaction of gas mixtures at the discontinuity. The evaporation spot was approximated by a finite difference grid in such a way that in the cells, the centers of which fell inside the contour of the spill spot, the boundary conditions of evaporation are set, and in them the iterative process of searching the back pressure is carried out until a given impurity mass flow is achieved through the phase that is adjacent to the evaporation spot. Using the developed model, The evaporation of liquefied hydrogen from an emergency spill spot in the shape of a rectangle was simulated at a gas station site near residential buildings. Fields of mass concentration of hydrogen in space near the epicenter of the accident were obtained for different wind speeds. The change in concentration along the velocity vector was also assessed. The resulting distributions of hydrogen mass concentration for different wind speeds are in good agreement with physical experiment data. It is obvious that as the wind speed increases, the hydrogen cloud is pressed more and more towards the surface of the Earth. The mass concentration of inflammable impurity is a dangerous flow parameter that can be used to estimate the power of possible explosion of the mixture. Not all explosive gases participate in the explosion, but only those whose mass concentration in the gas mixture is within the ignition limits of the impurity. The total mass of flammable gas that reacted gives an idea of the power of the explosion. In accordance with the model, at the moment of explosion of the gas mixture, the parameters of the mixture in the gas cells that participate in the chemical reaction are replaced by the parameters of the impurity detonation products. An area with high overpressure and temperature is formed, which leads to the emergence of a pressure blast wave that spreads from the epicenter of the explosion, gradually losing its intensity. The maximum overpressure and impulse of the compression phase in the shock wave front characterize the degree of harmful effects on humans and the environment. A person may receive injuries of varying severity and buildings may be destroyed. Finally, the following conclusions can be formulated. The mathematical model of liquefied combustible gas evaporation and explosion was developed. The model was validated against experimental data for hydrogen and propane evaporation and explosion. Non-stationary fields of dangerous combustible admixture mass concentration during evaporation and dispersion processes and the total mass of flammable gas were obtained for different wind conditions. The spatial distribution of maximum pressure was calculated, which can be used during deterministic analysis of shock wave loads on humans and buildings near the accident epicenter. Obtained information about explosion wave characteristics, maximum overpressure and impulse at wave front can be used in probabilistic analysis in order to evaluate the damage probability and individual risk caused by accidental explosion at high danger industrial objects. Thank you very much for your attention.